So let me first begin by talking about a classical problem in analytic number theory. So we have these generalized divisor functions. dk of n is the cardinality of the set of n1 up to nk natural numbers whose product is n. So then d2 of n is just the number of divisors of n. And then so if you look at this function, it oscillates tremendously as you go from one number to the next. So if you take a prime, for instance, then it's it's k. And then if you take like a prime power or a product of the Zing primes, it can be much, much larger. And so, but despite this, we believe that if we sum this function in some short interval, then its behavior will be much more regular. So the kind of the conjecture, I think, is that if we sum it over interval, it'll first equal the length of the interval times some kind of average value. For this is some polynomial of degree k. And then plus an error term, which is of size maybe the square root of the interval times n to the epsilon. Oh, maybe depending on k, epsilon. For short intervals. Or something like this should be true. But this is a
h to the what?
H to the 1/2 is what I'm suggesting.
So how do you order this? N and h, all of them goes to infinity?
Yes, yeah, where n and h are going to infinity, and then n is going to be much larger than h. Yeah, I mean, sort of if h is constant and n is going to infinity, then this is sort of trivially true because the divisor function is bounded by n to the epsilon for any epsilon. But you don't really have to have h go to infinity. But it's, yeah.
Do you have an idea what greater than h should be? Some fractional power bin, log?
Yeah, so you might, if you're more careful with defining this main term, like if you maybe define this main term as an integral of this polynomial, then I think the length of h, as long as it can be as long as you want and it won't matter. If you don't define it carefully, then there's going to be some upper bound. But I think this problem gets easier as h gets larger. As long as I state the main term correctly, which I didn't actually do, then it should be fine. Yes, you're right. Yeah. Well, yeah, and the leading term should be maybe n to the k minus 1 or log n over k minus 1 factorial, something like that. But I'm not going to consider this problem in my talk. I'm going to try to consider a function field analog. This is just going to be motivation. So what I'm going to consider, we're going to try and replace the integers with polynomials over a finite field. And so for the natural numbers, we're going to replace them with monic polynomials. Which is usually ends up being the nicest replacement in these kinds of situations. And so we're going to define dk of f to be the cardinality of the set of f1 through fk monic, whose product is f. Kfi is equal to f. And so the theorem is if we take f of degree n, and we take monic, and we take some h less than n, if I sum over, so the analog of a short interval, we're going to think of it as being, or short interval or 0, we're going to think of it as polynomials of small degree, so of degree less than h. And we're going to sum the divisor function of this like shifted integral dk of f plus g. So the length of this sum is the number of polynomials of degree less than h, which is equal to q to the h. And the polynomial that occurs in this case has a particularly simple form. It's n plus k minus 1, choose k minus 1. And the error term is kind of weird. So the error term is
these g's aren't monic.
the g's are not monic, yeah. We have this same n plus k minus 1, choose k minus 1. We have a k plus 2 to the 2n minus h. And then we have q raised to the power of h over 2 times 1 plus 1 over p plus 1. So where p is the characteristic. What do you say?
Big letters on the middle board.
Yeah. So, well, actually, the error term, the explicit error term, let's write it with explicit constant. So the error term.
Write the whole thing.
Sure. OK, so I'll write it a different way then. Degree of g is less than h, dk of f plus g minus q to the h n plus k minus 1, choose k minus 1, is at most 3, n plus k minus 1, choose k minus 1, k plus 2 to the 2n minus h, q to the h over 2 times 1 plus 1 over p plus 1.
You're claiming that they
What's
go.
k?
Dk, yeah. We have a dk,
That k.
yeah.
So they goes 3.
Yeah, the big O is 3 in the original thing. Yeah.
There's no large q or
This is true for any q, yeah. But it's trivial for q that are small relative to k. And so what I want to observe is this error term has a similar form. It looks like q to the h to the 1/2 times q to the n to the epsilon, where epsilon goes to 0, not as n and h go to infinity, but as q and as q and p go to infinity. So I get some estimate in the large n limit, and it's a power savings, and the power approaches square root cancellation as q and p grow. And the reason for this is, OK, here's the q to the h over 2, and then every other term we can see it gets smaller as p grows. So like, or as p grows or q grows. So this term gets smaller as p grows. This term, if k plus 2 is much smaller than q, this term is negligible. And this term is less than any exponential in n already. So this result so it almost completely verifies the functional analog of the conjecture, unless you really want to be a stickler and you want to make sure that this epsilon goes to 0 for every single choice of finite field. And so the strategy of proof is we're going to first express as counting solutions to equations, some system of equations over finite fields, over FQ. 2 is we're going to try to derive an estimate for the solutions from some vanishing of cohomology groups. Vanishing of many cohomology groups. And then we are going to get vanishing of cohomology from, it turns out, from controlling the singularities of these equations. So this kind of general strategy maybe should be called the like a homological stabilization method in number theory of function fields, that where we try to get estimates that hold not just in the large Q limit, but also in the large N limit by trying to control not just one cohomology group, but a whole series of cohomology groups. So it was used, for instance, in this paper of Ellenberg, Venkatesh, and Westerlund on class groups, this paper of Shende and Zimmerman on equidistribution in Bantu P1. And the particular kind of version of this method we're using is very similar to this paper a couple years back of Daniel Haast and Vlad Matej. And so the estimate that they get, so they applied this to a slightly different problem. They were considering the moments of this sum. So you would raise it to some power, and then you would sum over f. And then they get estimates for it, which were roughly of the strength of the Riemann hypothesis, and which, as they observe in their paper, were already known at that time. And so by applying the same method to a different problem, and those are the best possible estimates it's possible to get using this kind of technique on that problem. But by applying the same method to a different problem, we get a stronger estimate, which was not already known. And that's part of why I consider it to be very lucky, that's the title of the talk. So first, how does step 1 work? We want to focus attention on this term. And the first thing we want to observe is by the definition of decay. We can write the sum g in FQ join T. Degree g is less than h. Dk of f plus g is equal to the number of f1 through fk in FQ adjoint T, monic, whose product decay fi is equal to f plus g for some g, g of degree less than h. So the only thing that's going into this identity is there can be at most one g, which satisfies this equation. So I'm counting, summing over g is the same as counting if there exists a g or not. And then it's very natural at this point to break the sum into a sum over the degrees of polynomials. So this is equal to the sum over n1 through nk of this cardinality, f1 through fk and fk joint t, monic degree fi is equal to ni, satisfying this equation. I equals 1 to k, fi is equal to f plus g for some g. And then because the product of the fi's has to have degree n, that implies that the sum of the ni's must equal n. Now, because the number of possibilities, tuples n1 through nk that sum to m of natural numbers, is given by this binomial coefficient, it suffices to prove, if we count the number of f1 through fk, or monic, degree fi is equal to ni, such that prod I equals 1 to k fi is equal to f plus g for some g of low degree. And we subtract q to the h, that this is at most the same error term, but without the n plus k minus 1, just k minus 1. 3k plus 2 to the 2n minus h. Q to the h over 2. 1 plus 1 over p plus 1. So, oh, I forgot to say something. I'll say it later. And this we can express as naturally as a system of equations over a finite field. So what we'll do, we'll write fi as equal to t to the ni plus ai comma 1 t to the ni minus 1 all the way ii comma ni t times t to the 0. And then we'll write f as t to the n plus c1 t to the n minus 1 all the way to cn times t to the 0. And then this equation, so this, the equation is the product I equals 1 to k of this polynomial, t to the ni plus ai1 t to the ni minus 1, all the way down to ai ni, should equal t to the n plus c1 t to the n minus 1, plus, and so on. Except, because we're allowed to shift by g, we only check the leading n minus h plus 1 coefficients. So if the leading coefficients of this product are equal to c1 up to c n minus h, then there exists such a g which will make all the coefficients equal, and otherwise there won't be. So for simplicity, we write m is equal to n minus h, and this basically gives m equations, polynomial equations, in the n variables. C1 through Cn. Sorry, Aij. Because we expand this out, each coefficient is a polynomial, and we're setting it equal to one of the CIs. So because we've expressed this problem as solutions to some equations in a finite field, we can view it also as counting FQ points of some variety or some scheme. So this count, our count, is equal to x n m n1 through nk c1 through cm of fq, where that x is the variety defined by these m equations. Okay, and so the theorem, the Grothendieck Lefschetz fixed point formula, tells us that the cardinality of x over fq is equal to the sum over I minus 1 to the I times the trace of Frobenius at q on hi compactly supported of x fq bar q out. So we will derive our point counting estimate from 3 facts. So the first one, so to control the trace of Frobenius acting on these cohomology groups, we have to control the eigenvalues of Frobenius, and we have to control the dimension. So the first one is from Deligne. We know the eigenvalues of Frob Q on hi compact are at most q to the I over 2. Then to control the number of eigenvalues, we'll use the Betti number bounds of Katz, which implies, in this case, that the sum over I of the dimension of hic of x fq is at most 3 times k plus 2 to the well, n plus m is the same thing as 2n minus h in the new kind of variables. So this is because all this follows from is that we have m equations in n variables of degree at most k. And we get some kind of universal bound for the Betti numbers. And the third fact, which we can't use a universal result, and we have to put some work in, is that these HICs vanish equals 0 for I greater than n minus m plus, we'll look at the exact formula now, floor of n over p minus floor of n over, or that's actually not, n minus m.
Write bigger.
Yeah, I'll write bigger and I'll also write easier. I greater than n minus m times 1 plus 1 over p plus 2. Except for I is equal to 2 times n minus m, where it's one dimensional and is equal to QL of minus n minus m, which is a fancy way of saying that Frobenius acts on it, acts by q to the n minus m. So given these 3 facts, it's not so hard to see why this estimate is true. So we get a contribution of q to the n minus m, which is q to the h, from this top cohomology group. And then if we look at all the other cohomology groups, the Betti numbers are bounded by this, and the size of the eigenvalues is bounded by this.
You're going to explain 3.
Then I'm going to explain 3 next, yeah.
We'll keep on.
Yeah, so this is indeed where, well, yes, this is, the very end will be the lucky part.
The n minus m should be in parentheses.
I'm sure you're right, yes.
And will you see why it should go all the way down to square root cancellation? You just can't prove it? You have this 1 plus 1 over p?
I see. So it will look, when you see why, it will look like maybe it actually doesn't go down to square root cancellation in small characteristic. Like it's not really clear. The method is not really strong enough to give you a clear answer why it should or it shouldn't. It's plausible to me that it doesn't, but I don't know. So then for part 3, we can reduce to the case when n1, when k is equal to n, and n1 through nk are all equal to 1. So this will be the case where we're completely factorizing our polynomials. And the reason for this is that basically gives a finite covering of its variety, and cohomology can only go up when we pass to a finite covering. And that in that case,
Say again what you just said. Who's
Oh.
1 and who's not 1?
so the degrees, these ni's determine the degrees of the fi's. I want the ni's to all be 1. And then because the ni sum to n, then k has to equal n. And k is equal to n, and n1 through nk is equal to 1.
Wait, sorry, can you say it again?
So I'm reducing to the case where all these polynomials fi are linear. I can factor it, and factoring changes my variety, but it involves passing to a finite covering. And then the cohomology of the base will be like a summand of the cohomology of this finite covering. So I can show the vanishing upstairs.
Right, so that's the reduction?
Yeah,
You're not
that's-
going to tell us more than that?
Yeah.
I'm just going to say that we're reduced.
Yes. I mean, if you want to hear more, I can tell you more, but I think that's a. And then in this case, in that case, the variables will just look like there's going to be a1 through an, and the equations will be like the jth symmetric function of a1 through an. The elementary symmetric polynomials are equal to the jth constant.
And remind us how many SIs this is imposed on?
So, well, m for j is equal to 1 for j from 1 to m, where m is as n minus h in our notation from earlier. If these CJs were all 0, then this would basically be a cone on a projective hypersurface. And then I could use a result of Katz in the appendix to his paper with Hooley, which gives a bound for the cohomology of a projective hypersurface in terms of the singularities. And then what we can just show is that for an affine hypersurface, the same bound holds as long as you consider the singularities at infinity, which basically ends up showing that the projective case is the worst case. So I'll state something formally. Lemma is that Hj of this x fq bar ql is equal to 0. Thank you. For j not equal to 2 and j greater dim x plus the dimension of the singular locus of the vanishing set of these leading terms, the elementary symmetric polynomials, plus 1. And then it's convenient if you think about when the vanishing set is empty, then if you plug this in, if you interpret this as -1, then this is also true. We get vanishing above degree n in that case. Oh. So this is like the middle degree. We get vanishing above the middle degree if we also shift it by this dimension of the singularities. And so there's probably.
Sorry, when you say V, is it the affine or the projective thing?
I mean the affine. Yeah, so I could do V projective and then it would be a +2 here. But
you said something about having to take care of the singularities at infinity, but I'm not seeing them.
Oh, but if I'm taking the leading terms here, if I take the leading terms, the affine singularities correspond to the singularities at infinity of the original thing. So another way of, an equivalent way of saying it would be that I take, or no, actually this is probably a little stronger. I could instead say plus max of dimension of the singularities of x and the dimension of the singularities of the projective closure of x minus x itself. And then
Can you put a parenthesis somewhere after divising?
Wait. Like this? Yeah.
Singularities of the boundary?
Yeah, singularities of the boundary. Yeah, as a projective hypersurface or projective complete intersection. And then
Sorry, you said the second thing was stronger, but you put a max, so isn't this weaker?
The trick is that dim singularities of x has to be at most the dimension of the singularities of the boundary plus 1. And then the dimension of the singularities of the affine cone, of the cone on the boundary, must equal the dimension of the singularities of x bar minus x plus 1. So the affine cone dominates both of these.
And this is supposed to be a lemma for a general x?
It's for a complete intersection.
Okay.
And then this lemma.
No, it's a complete intersection.
So we'll calculate the dimension. Our calculation of the dimension of the singularities will show that that it had the expected dimension outside of the singular locus, and the dimension of the singular locus will be small enough that it's okay. What do I say?
I mean, maybe there's an argument that
Yeah.
putting some symmetric functions equal to something.
Oh yeah, right. No, sorry, you're right. No, yeah, right. It's faster to do that. Yeah, it's easier to see this as a complete intersection. So to show it's a complete intersection, you can do the opposite thing. Instead of reducing to the case where all the ni are 1, you can reduce to the case when k is 1, because you're just passing down along a finite cover, and that won't change the dimension. And then when k is 1, it's just obviously linear equations. So yeah, you're right. There's a direct argument that gives you the dimension.
And when p becomes large, then instead of elementary symmetric functions, you could do Newton things. And maybe make it clearer also.
Yeah. Yeah, it wouldn't hurt, certainly.
Since you are apparently needing to take p large eventually.
Well, no, but p is not large relative to n. It's large relative to k. So, if you, what is it? It's interesting for k to be 3 or 4, something like that. And then you don't have to take p that large. You have to take p, yeah. We definitely do not want to reduce to the Newton case, because then we wouldn't get anything in the large n limit. Currently, we get a power savings in the large n limit, just not quite full square root cancellation. So, let me sketch why is this true. Let's sketch it one way. So what you can do is because it's a complete intersection, you can form a family when it passes family with a generic complete intersection degenerating to x. And then for the generic complete intersection, we know this vanishing because it's smooth, and the thing at infinity is smooth, and it's easy to prove this vanishing. And so to show this vanishing for x, it's sufficient to show the vanishing for the vanishing cycles of this family. But the vanishing cycles are supported on these singularities. And then by the semi-perversity of vanishing cycles, you get a bound for the degrees in which they can appear on, depending on their dimension. And it gets you exactly this. So that's just precisely the argument, which is in this appendix by Katz to this paper fully. But you have to do this. You have to do the whole thing, because vanishing cycle only works right when it's proper. You have to do the whole thing to the compactified variety, which is why the singularities of the boundary also enter in. So it basically suffices to prove that in the case, so if we're just taking the singularities, dimension of the singularities of the vanishing locus of these polynomials E1, S1 through Sm. This is at most n over p floor function minus m over p floor function. Because if we expand this out, you get an n minus m, which is the dimension, plus 1 plus n over p minus m over p plus 1, which upper bounds this.
Sorry, 3 on the left, is it I greater than or greater equal?
It's greater than that. So the weird plus 1 shows up from trying to bound these floor functions. So I didn't want to write the floor functions in my earlier results because they look ugly. But in the actual, yeah. So now a tuple of points a1 through an is singular if and only if it turns out that the cardinality of the set of elements of your field generated by a1 and an has to be at most m minus 1. And then let me,
Sorry, what did the cardinality? What? The cardinality is set, right?
yeah, the set. So,
Set something to the field.
yeah.
What does generated by mean?
No, it doesn't mean generated by, I just mean the set of these elements. So not counting repetitions. So a singular point is a one where there's so many repetitions that this cardinality, which you think would be n, is actually less than n. This step is one part that's very much similar to what goes on in Haas-Simonet's paper. So let me just give the idea of why. So to calculate the singularities, we have to look at like the Jacobian matrix, the m by n matrix of derivatives of these polynomials, and we have to look at the rank. And they're singular when the rank is at most m minus 1. And then if ai is equal to aj, then the columns at I and j of this derivative will be the same, because these are symmetric polynomials. II is equal to aj. The derivatives in those directions have to be the same. So this cardinality is actually the number of different columns in this matrix. That shows why the leftward implication is true. But then it's not so hard to see that by like some kind of van der Monde argument, that the rightward implication is true as well. That if there's m different elements among these guys, then those m columns are linearly independent. It's not so hard to check, for instance, by computing the determinant, or by playing around with derivatives of polynomials. This implies the dimension of the singularities is at most m minus 1. And if we wanted, we could stop here, except we'd have to revise our earlier estimates to something worse. And what we would get in that case, we would get a bound for original divisor sum problem, which is exactly the same as the bound you can get by applying the Riemann hypothesis directly to this problem. So you would relate to the L functions and apply the Riemann hypothesis for these L functions. And so in the case where Haas-Simonet's study, this upper bound on the singularity dimension, it's easy to see it was sharp. So it was a similar set of equations, and this was inequality. So that they can't, by applying this method, they couldn't do any better than that. But what I consider to be lucky is that in our case, the dimension is actually smaller. And then for these purposes, it's going to be convenient to write the variables another way around. So we can write our system of equations. Product I equals 1 to n, 1 minus ai times u is equal to 1 plus o of u to the m plus 1. So I'm using the elementary symmetric polynomials backwards. So I've written it as being the lowest order term instead of the leading terms. So I've written it with a different variable. And so while everything previously was totally different from the way an analytic number theorist would approach the sum of divisor function, I do find it convenient now to borrow some notation from analytic number theory. So I'm going to use the big O notation. So where O of u to the m plus 1 means a power series in U, or polynomial in U, of degree starting greater than or equal to m plus 1. And then similarly for other. And so we have this equation, and we also know that there's a lot of repetition over here. And we'll use that to get better control on what the ai can equal. So what we do is we take the logarithmic derivative of both sides. So the logarithmic derivative of product is going to be the sum. So we're going to get the sum from I equals 1 to n minus AI over 1 minus AIU.
Product 1 minus AI.
It comes from these system of equations. I'm looking at the vanishing locus of these elementary symmetric polynomials. So the coefficients of this polynomial are the elementary symmetric polynomials.
I thought they were fixed to these values, CJ.
No, because I reduced, over here, I reduced to the case where the CJs were like 0. Because, yeah.
You did?
Um,
Did you talk to them?
well, I said only the leading terms. So over here, where did I write it?
I think this V, right? That was supposed to.
Yeah, V of just the elementary symmetric polynomials. So I didn't write SI minus CI here. I didn't write this, so I won't write it now either.
But in the statement of your lemma, right?
Yeah. Oh yeah. Here. Yeah.
Does it
Here's-
correspond to going to the boundary? Is it
Yeah.
to infinity?
Yeah. So I correspond to basically it's the same trick with the affine cone. I only had to consider the boundary points because the singularities away from the boundary are controlled by the singularities on the boundary.
So you mean a power series that starts at degree?
Yeah. Starting at degree n plus 1. I mean u to the a times u to n plus 1 plus b u to the n plus 2 and so on. Sorry about that. So. Oh, sorry, I have to finish writing this equation. So then if I differentiate 1 plus O of u to the m plus 1, I'll get O of u to the m divided by 1 plus O of u to the m plus 1. And this whole thing is O of u to the m. So because we're thinking of u as basically being very small. So now, this left side is a rational function, g1 of u over g2 of u. And the degree of g2 is at most m minus 1, because only m minus 1 different terms appear in the denominator here. Which means the degree of g1, because each term vanishes at infinity, the degree of g1 is less than or equal to the degree of g2 minus 1. So it's less than or equal to m minus 2. But because the right side is O of u to the m, that means that u to the m has to divide g1. And that means that g1 is 0. So now, so that means this logarithmic derivative is 0. This logarithmic derivative is 0.
So it just looks like you reduced to Newton symmetric functions. Because if you actually wrote out what that thing is a power series.
Yes, right. So, but I think if I had reduced to Newton symmetric functions earlier, I would have run into trouble maybe with the derivatives. I don't know, but yes, I agree that now there's a reduction to Newton symmetric functions at this step. But it's important that I take this logarithmic derivative, I think, after I already learned this fact about the cardinality, because I can then use it to control the left side. Because the logarithmic derivative is 0, that implies this product, I equals 1 to m. So if we're going to carry this to 0, by integration, this product would just have to equal 1, or I guess a constant. But it's not. We're not in characteristics of 0, so it merely has to be a pth power. So only the coefficients of powers of u that are divisible by p vanish. Now, how many powers of u that are divisible by p lie between n and m? It's exactly this. So that implies there are n over p minus m over p floor function parameters.
This product here, the last part here, that's up to n?
Oh yeah, right. Yeah, you're correct. That's up to n. Yeah, you can check that they are actually, except if, oh yeah, if n is much larger than m, then there could be such polynomials where the degree, the number of them, the number of distinct factors is not actually n minus 1. Because all these polynomials, the number of distinct AIs is at most n over p. But yeah, so it is sharp with m in a reasonable range. So that actually completes the proof, or at least the proof sketch.
So the lucky part was thinking of doing this?
Is that it works. So the lucky part is that you do this and the dimension gets much smaller. So if I had tried it on a different problem, like even if I'd been clever enough to think of doing this, I still might not have gotten anywhere. Yeah. And yeah.
So in some range, you say this really is the dimension of the singularity locus, but it could, of course, just be that this lemma is
not sharp. Yeah, it's a very. I mean, it's a slightly crude tool, and I think there might be other kind of variants of this problem where it's possible to do better and maybe to actually get a sharp or almost sharp bound on cohomology. But I have not worked that out yet. But let me try and give the application, because this is quite cool. So we're going to take chi characters from fq adjoint t mod t to the m plus 1. So we're going to work with basically Dirichlet characters over fq adjoint t, which have two special properties. They're even, meaning chi restricted to fq cross is trivial. And they are primitive, meaning that chi of 1 plus t to the m fq of t is not trivial. And then it's not too hard to calculate that there are q to the m minus q to the m minus 1 such chi. Just lost. So we can define the L function, the completed L function, ls chi, is equal to 1 over 1 minus q to the minus s, sum f in fq adjoint t. Monic chi of f, q to the minus s times degree of f. And so this is the local factor at infinity. So the second theorem. If we take 1 over q to the m minus q to the m minus 1, the sum over chi mod t to the m plus 1, primitive even. So I take ls chi and I raise this in power r without taking the absolute value, then this is equal to the expected main term, or let's take L1/2 chi, which is 1 over 1 minus q to the minus 1/2 raised to the power r plus central point, yeah. There's an estimate also for non-central points, but okay, let's see if I can write it big enough over here. Plus O of m to the r plus 2 to the rm minus r plus m, q to the rm minus r minus m over 2p plus 1 times q to the minus m over 2. So this q to the minus m over 2 gives this term. If I just had this term, it would be square root cancellation in this family of L functions. And then the remaining terms, in particular these two, are both dominated. They're lesser powers as long as m, q, and p are sufficiently large with respect to r. So again, this is an estimate that approaches square root cancellation in a large m limit, and it approaches it as q and p go to infinity with r. As far as I know, this is the first non-trivial estimate for an arbitrary high-power moment of a family of L functions over number fields or function fields that works in a large degree limit rather than the q aspect. Yeah, of course. Right. In function fields. I can just say, yeah. As far as I know, it's the first in function.
What did you do on this with
Oh.
4? Just 4? 6?
Yeah, it was the fourth moment for quadratics.
Oh, for quadratics.
Yeah,
Yeah.
just for quadratic.
Is it a problem to put in absolute values?
Yes, it is a problem. So what I could do, I can also do something if you put a single copy of L1/2 chi conjugate, but if there's more than one copy of L1/2 chi conjugate, this method does not work. So it's somehow very crucial that we're doing sums of divisor functions in short intervals, and we're not doing like second moments of sums of divisor function in short intervals. That's much harder. Yeah, so the only thing that, I don't know, well, actually not the only, but the main thing you might not like about this estimate is that we do not have an absolute value in here, and we can't put them in.
That's with the quadratic case, that's not an issue.
Yeah. And then I claim it's actually pretty straightforward to deduce this from the result that I stated at the beginning. So the sort of trick is that the field FQ adjoint T has an automorphism. T goes to 1 over T. And if you apply that automorphism to these characters, instead of depending on the lowest order coefficients of your polynomial, they'll depend on the leading order coefficients. And then these characters will be constant on short intervals. So they're considered the short interval family of characters. And then if you just kind of expand this sum and exchange the order summation, and then use the divisor function estimate, you get exactly this. Yes, and I have no time to say anything else, so I will stop.